In this video, we are going to go over how to graph linear inequalities. What is a linear inequality, you ask? Well, it's basically a linear equation, but instead of having an equal sign, you have an inequality sign. So that could be greater than or equal to, less than or equal to, less than, greater than. We're going to go over how to graph this out. And then the second part of this video, I'll go over a second inequality that will go over how to graph out one that has a less than sign. So let's go over this. Now, before I dive into this guide, I want to go over the main idea, which is why do we need to know how to do this? We use linear inequalities to describe entire regions of a graph, entire spaces, just like we used number lines to describe entire sections of a number line. So way back when, you had something like y is less than or equal to 4, and you took a graph. And from there, since it was less than or equal to 4, you had a number at 4. You had a closed circle because we included 4, and then shaded everything to the left. And we describe this as all numbers to the left of 4, including 4. If we had greater than, we had everything to the right. Well, it's really not much different when we're graphing linear equations, except instead of shading in one dimension, we're shading in 2 dimensions, right? Because you've got x's and y's. Okay, so as I said, not so bad. Let's dive into this. The first idea is this. You're basically taking this inequality and you're visualizing it as this. You're saying, let me graph out y equals 2x minus 5. That's going to be your boundary, right? So that's going to be like the circle you have in one dimension, except it will be a line because we're in 2 dimensions. So graph out y equals 2x minus 5 first. 2x minus 5 has a y-intercept of -5 and a slope of 2. So that's rise 2, run 1. Okay, so our y-intercept is -5. That's down 1, 2, 3, 4, 5. Right there, beautiful. And then we are going to rise 2 and run 1. Rise 1, 2, run 1. Rise 1, 2, run 1, and maybe I'll do one more. Up 2 over 1. Now, before you actually put in the line, what's a little bit different about inequalities than lines is that we have a decision to make. We need to either do a solid line for our boundary or a dotted line for our boundary. It's the same as determining whether or not we had a closed circle here because it's or equal to, or an open circle if it had been just strictly less than. So in that case, we would have had an open circle at that point. Well, when you have or equal to, you have a solid line because we are including, we're saying all y values more than or equal to that line. So if it's or equal to, you have a solid line. If it's not or equal to, you would have a dotted line because then you're saying all y values strictly more than, but not equal to that line. It's just like the open and closed circle. So we have or equal to, so I will do a solid line. Like that. So that's my boundary. Now that I have my boundary, just like we shaded on a single dimension, we now need to shade on 2 dimensions. You can accomplish this correctly in 2 different ways. Way 1 that's often taught is just by reading it and thinking about it. Since it's in slope-intercept form, we're saying all y values, and I'll make this now a greater than or equal to, more than, above 2x minus 5. What are all the y values above this line? Well, that would be all the y values here. So you literally are just shading all of that area. So what you would do is you would take a marker, a pencil, you can shade it. I just do a couple lines, but it's all of this area here that is getting shaded, everything above it. Another way you can do this is by using a test point. Now, what does that mean? Well, you pick a point that is on either side of this boundary right here. And if that point when plugged into the inequality is true, then we shade that part of the graph that has that point. If that point is not true in that inequality, then we don't shade in that part, we shade in the other side. An easy test point, if it's not on the line, you would never want to test a point on the boundary, would be 0, 0. So here we go. Let's plug in 0, 0. So I've got 0, 0, and I'm going to test it into the inequality. So y is equal to 0 is greater than or equal to 2 times 0 minus 5, We simplify that. 0 is greater than or equal to 0 minus 5 is negative 5. Is that a true statement? Is 0 greater than or equal to negative 5? Yes. So what that means is the point 0, 0 right here is true. It makes the inequality true. So we're going to shade in all of the region that includes 0, 0. Either way you go about shading, whether or not you use the test point idea or you use the idea of above or below, hopefully that will get you to your correct answer. Now, I said earlier in this video that we'll do 2 clips in this video. I think I'm going to separate this. Stay tuned and watch a second video that will go over what happens when we have less than. And we'll check that out in a little bit. Come on with me over to another video for that. In this video, we are going to go over how to graph a linear inequality when we have a strictly less than sign. In a previous video, we went over how to graph greater than or equal to, and we talked a little bit about dotted versus solid lines, that is. So let's jump into this. Remember from the first video that you went over with graphing linear inequalities, the first thing we do is we're basically visualizing this as y equals 3/4 x. Well, let's draw out that boundary. So this has a y-intercept of technically 0, right? It's like you've got plus 0 over there. So your y-intercept is 0, and you're going to rise 3 and run 4. So our y-intercept of 0, right there. And then we're going to rise up 1, 2, 3 over 1, 2, 3, 4. Perfect. Rise 3, 1, 2, 3, run 1, 2, 3, 4. And let's do one more in the other direction just for fun. Down 1, 2, 3 over 1, 2, 3, 4. Beautiful. Now, before we draw in our boundary, we need to make sure that it's either dotted or solid. As was discussed in video 1 with linear inequalities and graphing them, I'll discuss again the relationship between this and old school graphing on a single dimension number line, right? So let's say that you had the inequality y is less than, I don't know, 2. So you got the value 2 here. You would have an open circle because you do not want to include the value of 2. And we would shade everything to the left of 2 because it's all values to the left. Well, now we're in 2 dimensions, so we can't just shade to the left or to the right. We're going to shade either above or below all the y values. And we can't just draw open circles because we don't have a single dimension. So to represent open circles, we would do a dotted line. So here this is not or equal to, it's saying all y values less than. So we're going to have a dotted line for our boundary. So I literally just go dot, 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 dot. Some people like to draw out the line, and then what they'll do is they will erase little bits in between so it's a dotted line. So that dotted line represents the less than, not less than or equal to. If this had been greater than, this would also be a dotted line. It's if you have an or equal to symbol that you then do a solid line to represent you're including all the values on that boundary. Okay, all right, let's get that out of there. Now, how do we learn what to do with shading with less than? Well, there's 2 ways. The way I prefer is I read it literally, and I look at it and I say all y values less than, below the line 3/4 x. Well, below the line would be here. So that would be all of these values there. So it's literally all of the points in this space will be solutions that make this linear inequality true. Another thing we could do is pick a test point. So let's pick a test point. So I'll do, well, I can't do 0, 0 here. And the reason being, like I did in the first video, the reason being that I can't pick 0, 0 is it is on the boundary. That's only going to show me that 0, 0 is on the line, not whether or not it makes the inequality true or false for all the points above or below. So I realize that these are my solutions, but I'm going to pick a point above this boundary. Let's pick, I don't know, 0, 2. Let's test that. The reason why I picked that is x equals 0 is easy to plug in. So I'm going to do a test point of 0, 2. And we want to see if 0, 2 makes that inequality true. So I plug in 2 for y is less than 3/4 times 0. So the question is that a true statement? Well, we would get 2 is less than 0. Is that true? No, 2 is not less than 0. So that means that this point is not in the solution set. It does not work in that inequality, which means all points in this entire what's called a half plane, it's literally half of the coordinate plane here, do not work, which means all the points on the other side of the boundary do work. So we would shade in all of these points. That's it. So if you were to pick any point in this region and plug it in, it would be a true statement. That's all, folks. Graphing linear inequalities. I got excited about graphing systems of linear inequalities. That's in a later video, or even for you, if you're taking the pre-algebra class right now, that might be in a later math class. Graphing linear inequalities is something that you guys can rock and roll with using the basic ideas that we've gone over in videos 1 and 2 of graphing linear inequalities.